Namaste. Welcome to the next video of Machine Learning Techniques course. In this video, we'll discuss optimization techniques for linear regression model. The key calculation in optimization is the derivative of loss function with respect to the weight vector. Here, we will look at a couple of useful identities for this derivative. The first identity is concerned with derivative of a linear function. The derivative of a linear function wx with respect to w is equal to x, and this derivative is same as the derivative of couple of other linear functions x transpose w and w transpose x with respect to w. Let's look at another identity which is about derivative of a quadratic function. The derivative of the quadratic function with respect to w is equal to 2xw. We will be using these derivatives while calculating the derivative of the loss function with respect to w. So you may remember that our loss function is half times the difference between the predicted value and the actual value. We take the transpose of the difference and multiply it with the difference vector. So that gets us the loss for the linear regression problem. So what we have done is we have taken this particular equation and applied bunch of algebraic manipulations before actually applying derivative to individual terms. So the first step, we use the identities from the matrix world and we rewrite the first term as xw transpose minus y transpose and multiply it with xw minus y. Then this particular term can be rewritten as w transpose x transpose, and in the next step what we do is we essentially do multiplication between these two terms. So w transpose x transpose into this particular term minus y transpose with this particular term, which is essentially we are multiplying this term by individual terms from the first term. So after doing couple of more algebraic manipulation, we reach to this particular step, and here we apply a small trick. So we rewrite this particular term, which is y transpose xw, as w transpose x transpose y, and by doing that we basically bring this particular term in the same form as this particular term. And this helps us to arrive at w transpose x transpose into wx minus 2 times w transpose x transpose y plus y transpose y. And then we essentially apply the partial derivative operator on individual terms. And here we use the identities that we saw in the previous slide and obtain the derivative as x transpose xw minus x transpose y. By taking x transpose common, we get x transpose into xw minus y. So this is the derivative of the loss function with respect to the weight vector. And by the way, this is a partial derivative. It is del jw del w. Now after obtaining the partial derivative, how do you obtain w? So we use couple of methods for that. The first method is the method of normal equation, and the second method is the method of gradient descent. In the normal equation method, we set the partial derivative to 0 and then solve and then solve the resulting equation with analytical methods to obtain the weight vector. Whereas in gradient descent method, we iteratively change the weights based on the partial derivative of the loss function at that point until we converge. We'll look at the convergence criteria of gradient descent in a bit. So let's look at the normal equation method. We set the partial derivative of the loss function with respect to the weight vector to 0 and solve for the weight vector. So that's the crux of the normal equation method. So let's set our derivative or our partial derivative to 0. So this is our partial derivative. We set that to 0, and then what we do is we do some algebraic manipulation. So we essentially take this particular term on the right hand side, and then we separate the w out and take this particular term on the right hand side. So ultimately we can get w by x transpose x inverse x transpose y. So by this particular equation we can obtain the optimal value of w for the given training set for linear regression model. Let's look at the other method, which is gradient descent method, which uses iterative optimization approach in order to find the optimal value of w. So let's first look at the non-vectorized version, and then we'll look at the vectorized version. The first step in gradient descent is about randomly initializing the weight vector. One possible initialization that works in model like linear regression is that we initialize each component of the weight vector to 0. So in other words, we initialize the weight vector with a 0 vector. In the second step, we iterate until convergence. Now in second step, it's a loop which runs until convergence, and we'll define convergence criteria in few slides. The first step there is to calculate the gradient of the loss function with respect to individual weights. So there are m plus 1 weights, w0, w1 all the way up to wm. And these partial derivatives are namely partial derivative of jw with respect to w0, with respect to w1 all the way up to wm. And we have shown the form of this partial derivative for your reference over here. The partial derivative of the loss function with respect to ith weight is in general can be given by, so let's say I is equal to 1, so we look at partial derivative of the loss function with respect to w1. So it is essentially the difference between the predicted value and the actual value, right? So this particular equation over here gives us the predicted value. So this is the difference between the predicted value and the actual value, and we multiply it with the value of the feature itself. Okay, so the form of the partial derivative is exactly the same for all the features, for all the weights. So only change is that the multiplication factor changes. The multiplication factor is essentially the feature corresponding to the weight. So for ith weight, we have a multiplication factor. We essentially multiply with ith feature. So in order not to confuse you with I, let me use j as a subscript. So for the weight wj, we multiply with feature xj. Okay, xj, the feature xj of ith example will be multiplied over here. For example, for the weight wm, we are multiplying it with feature xm. Okay, in case of w0, which is bias unit, right, we multiply it with feature x0, which is a dummy feature, we set it to 1. So the derivative, the partial derivative of the loss with respect to the bias term is nothing but a summation over all training example the difference between the predicted value and the actual value. So once we calculate these partial derivatives, we use them in order to calculate the updated parameters or updated weights. So the new weight or the new value of the weight is set to, so remember this is a set operator and not equal to operator, it is set to the old value of W0 minus alpha times the partial derivative of loss with respect to W0 and so on. So for W1, we subtract the old value of W1, we subtract the loss, we subtract the partial derivative of loss with respect to W1 into alpha from the old value of W1. In order to obtain a new value of Wm, we use the old value of Wm and subtract the partial derivative of loss function with respect to Wm weighted by the learning rate alpha. So alpha is a learning rate. So alpha decides how much quantity or how much of the partial derivative we are going to subtract from the existing value of the weights. And at the end, we update these parameters simultaneously. Remember, now we have equal to sign. Earlier we had set sign. So when we were using set sign, we were not actually setting them to the new value right away. We were actually we were updating the new values, but we set all those new values we update the parameters simultaneously in the last step. After this step, we have a new weight vector. So this is an important step and important observation that you should note is that the weights are updated to the new values simultaneously in the last step of gradient descent. Until then, we use old values for predicting labels of training examples while calculating the partial derivative of the loss with respect to different weights. So this is an important note that you should remember, that weights are updated simultaneously in the last step of gradient descent, whereas weights are set to the new values before that, and they're updated simultaneously in the last step of gradient descent. Let's look at the vectorized version of gradient descent. So again, in vectorized version, right, we will have to come up with a gradient update, right? We'll have to come up with a weight update, and the weight, the next value of the weight is set to the old value minus learning rate times the partial derivative of the loss function with respect to the weight vector. And we know this particular quantity, right? We had calculated this, so we substitute the gradient of the loss function with respect to weight vector in this equation, and we obtain wk plus 1 is set to wk minus alpha times the partial derivative of the loss with respect to the weight vector. So by performing some algebraic manipulation, again this comes out to be wk minus alpha times xt into xw minus y, and this xw is nothing but a predicted output. So the new values of the weight vector are set to the old values minus alpha times xt into the difference between the predicted output and the actual output. Got it? So the vectorized implementation makes sure that all parameters are updated in one go simultaneously. Let's visualize the gradient descent moves. So for this, we'll use a simple model as usual involving a single feature. So we have a model of the form y is equal to w0 plus w1, x1. And then the loss, which is sum of squared error, is equal to half sum over all training examples, the square of difference between the predicted value and the actual value. So here we represent the loss landscape in terms of the loss surface, and here we have the contour representation of the same loss landscape. We talked about contour representation in the last video. So you can see that in loss landscape we have three axes. One is W0, second is W1. These are the weight vectors of the current model, and then there is a loss. Whereas the contour plot is in the plane of W0 and W1. So the x-axis is W0 and y-axis is W1, which is the other weight. And you can see that the optimal point is denoted by this particular star or this particular point over here, which is the corresponding point over here in the loss surface representation. And you can see that we start in some random point on the loss surface where we have a very high error or very high loss, and from there we basically make different gradient descent moves and finally reach the optimal point, the point where the loss is the least on the loss surface. Getting it? So this is how the linear regression, so this is how the gradient descent make moves in the loss landscape. So gradient descent is a very generic optimization algorithm that can be used for learning weight vectors of most of the machine learning models. And gradient descent obtains optimal weight vector by making small changes or adjustment to their values in each iteration that is proportional to the gradient of the loss function. Once the gradient descent reaches the minima of the loss function, we obtain optimal weights corresponding to the minima. Let's talk about the convergence criteria of the gradient descent. We declare the convergence of the gradient descent algorithm if the weight vector changes by a very small margin across successive iterations or in last few iterations to make it a bit more robust process. Or if the first criteria is not getting met, we have an alternative criteria where we stop training after a fixed number of iterations. So we use one of these criteria or either of these criteria for declaring the convergence of the gradient descent algorithms. So there are a couple of practical questions while implementing gradient descent algorithm. One is, how do we set the learning rate alpha, and how do we decide on the optimal number of iterations? So you can call these parameters as hyperparameters of the gradient descent algorithms. We do not optimize these parameters like the weight vector. So these parameters have to be specified by the designer of the algorithm. So that's why they are called as hyperparameters. So let's first look at fixing the learning rate alpha. So typically what we do is we try many different values of alpha. We start with a very small value and subsequent values are 10 times the previous value. That's how we fix our set of alpha values that we want to try for the gradient descent algorithm. And then for different alpha values, we can study the convergence. Here you can see the convergence characteristics of two gradient descent runs. In the first case, we are using a learning rate of 0.0001, and in the second case we are using learning rate of 0.001, which is 10 times bigger than the learning rate used in the top run. and you can see that the top run takes longer to reach the point, right? This is the point which is where we are supposed to reach. The gradient descent run with alpha equal to 0.001 reaches this particular point faster than the other run which is on the top, and that happens because we are taking baby steps, right? We are taking baby steps towards this particular point because of a small learning rate. Got it? So this is what happens if you have a very small learning rate. If you have a small learning rate, it takes you longer to reach the optimal point. Whereas if you have slightly larger learning rate, then you reach the desired point or the optimal point faster. Does that mean we should try very high learning rate? No, that could be detrimental. There are other problems that we will see shortly with very high learning rates. So such a visualization based diagnosis works because we had a very simple problem, right? We had a problem with, we had a linear regression problem involving a single feature. So we could afford, or we could, it was possible for us to draw such visualizations and examine how things are working. But when we have a large number of features, as in real world problem, such a visual diagnosis is just not possible. So in such cases, we should be using learning curves, and they are our best friends in general case. So let's try to see how to diagnose the problems with alpha, the learning rate, based on the learning curves. So here we have plotted learning curves for three different values of learning rate or alpha. Here we use the value of alpha to be 0.01. Here we use the value of alpha to be 0.1, and here it is 0.5. This value is 10 times larger than the alpha value over here, and this value is 5 times larger than alpha value over here. What do you observe? After first 50 iteration, alpha equal to 0.1, the middle gradient descent run has the lowest loss. And you can also observe that this loss has decreased. This loss has decreased very sharply as compared to the one at the left. The one on the left hand side, the leftmost gradient descent run with alpha of 0.01, you know, the loss which is on the y-axis, the loss decreases very slowly compared to the middle one, right? Whereas if we use a very high learning rate, I told you that it may not be a good idea always to use a very high learning rate, because when we use very high learning rate, there could be a possibility that we might jump over the desired point, which is the optimal point, and we basically diverge, and that's what you can see in these learning curves. When the linear regression model is getting trained properly, the loss reduces after every step of gradient descent. But in this case, instead of reducing, the loss is going up after every step of gradient descent. And if you ever see such a behavior in learning curve, there is a serious problem with the learning rate choice. And when you see such a situation, the best way is to reduce the learning rate and restart the training of the algorithm. So you can see that when we had a small value of learning rate, the loss was decreasing very slowly. When we had too large value of the learning rate alpha, the loss was rather increasing. And when we had just right value of alpha, we were getting a faster reduction in the loss. Let's see how to diagnose these problems based on the learning curves. We had talked about it briefly in the previous slide. So whenever we have small alpha or small learning rate, the loss either does not reduce or reduces very slowly after initial few iterations. So what you can do is, as you start training your model, you should keep observing your learning curve. And if loss does not reduce, or if it reduces very slowly, you can conclude that probably you have too small learning rate or alpha. So in that case, you should stop the training and increase alpha typically by 10x, restart the training, and again observe what is happening with the learning curves. Whereas, if you observe that the loss is increasing rather than decreasing after few iterations, after first initial iterations, you should conclude that you probably have too large value of learning rate. In that case, again, you should stop the training, decrease the value of learning rate typically by 10x, and then restart the training and observe the behavior of the learning curves, right? And see whether you see any of these problems again, and then again you have to repeat, right? You have to adjust your values of alpha and restart the training. The second hyperparameter was about number of iterations. So if we had too few iterations, what happens is, if we do not give enough time for gradient descent to run, it will not reach to the optimal solution. So it will normally stop short of optimal solution, and we will get some kind of a suboptimal solution, which may not give us the best possible performance on the training set as well as on the test set. On the other hand, if you have too many iterations, what happens is, once the gradient descent reaches the optimal point, it still keeps on computing the updates where the derivative is very close to 0. So we are not really updating the weight vector, but we end up wasting computational cycles. In practice, we set the number of iterations to a sufficiently large number, but add a convergence criteria. The convergence criteria make sure that we terminate the gradient descent loop as soon as the gradient vector becomes smaller than some threshold epsilon. So that was about gradient descent. In the next video, we will see some of the variations of gradient descent that are used in practice and that helps us in speeding up the training process.